Hi everyone, a few notes before we get started with this video. You can change the settings with the YouTube video, so you could add captions by clicking in the lower right corner where it says CC. You can change the video speed if you think I'm talking too slow or fast by clicking on the gear icon in the lower right, selecting playback speed and then adjusting to either lower speeds with the decimal places or higher speeds greater than 1. So let's get to it.
In this video, you'll learn how the air bubbles trapped in ice over millions of years help scientists understand atmospheric carbon dioxide concentrations over geologic history, explain how scientists use the isotopic composition of ice cores to understand temperatures in geologic history, and interpret rates of change by using 2 points to calculate the slope of a graph. So you just looked at the Mauna Loa dataset, and that covers a long time relative to the length of one semester, for example, but it only provides information about recent history. The Earth is over 4.5 billion years old, 4,500 million, and the last ice age took place from 110,000 years ago to about 12,000 years ago. At peak glaciation, about 22,000 years ago, the world looked different. The gray areas on this map, including the northern US and Canada, were covered by ice, while the southern US was covered by coniferous forest and grasslands. Pause the video and think for a minute about how you think we might be able to compare recent data, like the data from Mauna Loa, to geologic history. When the video is paused, click on Think on the right side of the screen to answer the question. To find the answer, we'll need to prepare. You'll need a parka, sleeping bag, lots of warm clothing. We're going to Antarctica. So this is a photograph of the Vostok Research Station in Antarctica. And these photos show some of the process of drilling for an ice core, which is one way that scientists can learn about Earth's climate and atmosphere in the geologic past. Think for a second. How could the air bubbles trapped in ice give us information about the past temperature and carbon dioxide concentration? Pause the video and click on Think on the right side of the screen to answer this question. I mentioned that scientists can use ice cores to learn about Earth's past climate and atmosphere, but let's take a closer look at how that works. On the right, you're looking at a very close-up image of air bubbles trapped in an ice core. On the left, you can see how the pressure of accumulating snow compresses ice particles deeper in the core over time. Eventually, the air bubbles are sealed off by ice, preserving the atmosphere of that moment. To maintain the ice cores once they have been drilled, they must be kept in a sub-zero storage facility such as the one shown here on the left. At the Ice Core Lab, samples can be prepared for analysis by splitting and sectioning the cores as seen in the lower right corner. In addition to being able to analyze the gases trapped in the air bubbles, we can also learn about past temperatures from ice cores. One way to determine the past temperature is by examining what isotopes of oxygen are present in the water molecules that make up the ice crystals. You can think of isotopes as different types of the same element. The difference between isotopes of a certain element is the number of neutrons each isotope has. Like protons and electrons, neutrons have mass, so an isotope with more neutrons will be a little bit heavier than an isotope with fewer neutrons. For the most part, all isotopes of a certain element will behave the same way in chemical reactions. However, small changes in the mass of an isotope can make a chemical reaction happen a little bit faster or slower. Evaporation is a little bit easier for water molecules made up of oxygen-16, the lightest and most common isotope of oxygen, than it is for water molecules made up of oxygen-18, the next most common isotope of oxygen. If you think of an ocean containing a mixture of light and heavy water, you can see in this image that the light water will evaporate faster. In interglacial or warmer periods of time, the water falls as rain and runs off back to the ocean. But in glacial periods, that light water gets trapped in snow and ice on land, and a relatively larger amount of heavy water returns to the ocean. So, in an ice core, glacial periods will contain more light water, and interglacial periods will contain more heavy water. Next, you're going to graph the temperature data from the Vostok ice core, but there are a couple of things to look out for. This example dataset is just to help you get situated. BP means before present. Where is the present time on this graph? Pause the video and click on Think on the right side of the screen to answer this question. Hopefully you said that the present time is at 0 BP on the left side of the graph. To examine the fastest rate of change in the Vostok dataset, you'll need to identify the area of the graph with the steepest slope. On this example dataset, where do you think that is? Pause the video and click on Think on the right side of the screen to answer that question. I think it's here, between 50,000 and 55,000 years BP. In your graphing program, if you hover your mouse over the data point you are interested in, it will give you the x and y coordinates of that point. Write down the coordinates of the 2 points you think show the fastest rate of change in the Vostok dataset. Once you know the 2 bookend points for the steepest slope on the graph, you can calculate the slope a couple of ways. You can make a new graph, plotting only the data from the first point to the second point. In our example dataset, that's from 50,000 BP to 55,000 BP, and calculate a trend line as you did before. Alternatively, you can estimate that the slope of the line connecting those 2 points is approximately equal to the trend line you would get. To find the rate of change based on the slope between 2 points, you'll calculate rise over run. The formula is y2 minus y1 divided by the difference of x2 minus x1. But don't forget about your units. In our example data, rise over run gives us 16 minus 25 units of our variable of interest divided by 55,000 minus 50,000 years BP. This simplifies to negative 9 over 5,000, or negative 0.0018 units per year. So that would be the fastest rate of change in this dataset. But remember that the past is on the right side of the graph, which is different from how you might be used to looking at graphs. So as you move forward in time from right to left, you can see that the value is actually increasing. That's all for this video. To review, you should now be able to explain how the air bubbles trapped in ice over millions of years help scientists understand atmospheric CO2 concentrations over geologic history, explain how scientists use the isotopic composition of ice cores to understand temperatures in geologic history, and interpret rates of change by using 2 points to calculate the slope of a graph. Pause the video and click on Think on the right side of the screen. Thanks for watching.